Traditional statistics, which are used in many scientific disciplines, rely heavily on p-values. As it turns out, there are many problems with p-values despite their widespread use. Let's look at a few situations to show how easily p-values can be influenced. As is covered in every introductory statistics class, p-values of less than 0.05 are generally considered statistically significant. When we say that p needs to be lower than 0.05 to be significant, what we're saying is that we'll accept a 5% error rate. 5% of the time, p will say that there is a statistically significant difference when really that difference is just randomness. So let's test this. I'll generate two sets of 10 random numbers and then compare. Is there a significant difference between the two sets? On any one trial like this, there is a 5% chance of finding a statistically significant difference. But what if I did this 20 times? I should get about one instance in which random numbers elicit a significant p-value. In my own case, it took just 9 trials to find an example of randomly generated numbers being statistically different. Indeed, we should expect that about 5% of the significant p-values in published research are likely false positives. It's important to understand that if I keep doing comparisons, I'm going to find significant differences, randomly. This is far from the only issue with p-values, however. They are also highly reactive to sample size. Imagine that I generate 2 more sets of random numbers. This set of numbers will produce a mean difference of 1.7 between the two groups. When you run a t-test on these values, you find a p-value of 0.25. That's not significant. What if I duplicated the first set of data to 10 more participants in each group? When we only had 10 participants, Group 1 had these values. The new participants have the exact same values as the old participants, we just have more of them now. If we do exactly the same thing for Group 2, then we still have the exact same Group 1 average, the exact same Group 2 average, and the exact same mean difference. The only thing that we did differently was that we increased our sample size. Think about this critically. The groups are exactly as different as before. They're just larger. What should happen to the p-value? When the sample size is 20, the p-value is 0.25. But when we double the sample size, we suddenly get a p-value of 0.09. That's still not significant, but it is dramatically lower. So what if we duplicate our data again? What if we add 10 more participants to each group for a total sample size of 60? What's going to happen? We will still have the same Group 1 and Group 2 averages. We still have the same mean difference. Now, simply because we added more participants, we found a statistically significant difference. This demonstrates that if you increase your sample size, you will decrease your p-value. Let's look at one final issue. In this example, we'll have 2 groups of 50 for a total sample size of 100. In Group 1, the first participant has a score of 1. Everyone else in that group has a score of 2. I'm going to do the exact same thing to the other group. So to be clear, both groups have the exact same data at the moment, and the p-value would equal 1. What happens if I change just 5 more participants' data, participants 52 through 56, to a 1 instead of a 2? In this situation, the group's averages are still nearly identical, and the mean difference is just 0.1. Despite this very small mean difference, our p-value is 0.02. That's significant. Let's hammer this point home. 90% of our sample answered the exact same way. And yet we are still finding a statistically significant difference. This means that sometimes when we use p-values, we will find statistical significance that means nothing practically. Don't despair. There are ways to deal with all of these problems, and a lot of the scientific literature does take these issues into account. But we should be aware of the ways in which p-values may react to various situations. And even if a lot of published research accounts for issues with p-values, not all scientists do. This we can improve.